Welcome to the public lecture of the General Assembly of the RASC 2015. I'd like to welcome all our members who are here from across Canada. I'd like to welcome any of the public that have come, and I know there's a number of people here as well from the Halifax Astronomy Meetup Group, so welcome to coming out to this event. Thanks for coming, and I hope you enjoy the evening. My name is Paul Gray. I'm the Center President of the Halifax Center of the RASC. I have a few house cleaning items to attend to first. First of all, the exits or the entrances you came in at the right and the left of the auditorium are your primary exits. On either side of the curtain, straight through the back, there are two emergency exits should we have to use them. Washrooms are, again, back out the hallways that you came in. The left side, well, my left side, your right, is the men's. The opposite side is the female. I think that's most of the house cleaning duties. I'm going to introduce James Edgar. He's the National President of the RESC. He will give you a bit of a background on who we are, what we do, and as well as the lecture you're about to hear tonight, and that is who it's named after and why we do this memorial lecture every second year. And with that, I will pass things off to my good friend and President James Edgar. Thank you.
Wow. Good evening. What a nice looking crowd. And for the members of the public who are here, this is a public lecture. So I want to tell you a little bit about the Royal Astronomical Society of Canada. We were founded in 1868 in Toronto. And we consider ourselves Canada's leading astronomy organization, bringing together over 4,900 enthusiastic amateurs, educators, and professionals. In addition to many national services, our 28 centers offer local programs all the way across Canada. Our vision is to be Canada's premier organization of amateur and professional astronomers, promoting astronomy to all. Our long history has been enriched through the hard work of hundreds of volunteers and professionals, and one such person was Ruth Josephine Northcott, who unfortunately died young at the age of 56 in 1969. She was one of those women who were called computers in the old days. She graduated from the University of Toronto in 1934, followed by her master's degree in 1935, whereupon she was promptly appointed to the staff of the David Dunlop Observatory in Toronto. Her primary work was in radial velocity measurements of stars in spectroscopic binary orbits. In 1983, minor planet 3670 was named Northcott, commemorating her significant contributions to astronomy and science. Obviously tireless, Ruth Northcott was the assistant editor of the journal and the assistant editor of the handbook at the same time. She eventually succeeded Dr. Clarence Chant as the handbook editor in 1952, and her last press run for the 1970 edition was 12,000 handbooks. In addition to all that, she was the RASC president from 1963 to 1965, and truly an inspiration to all who knew her. It is small wonder then that the Society honors her with the Ruth Northcott Memorial Lectures held in odd-numbered years, alternating with the Canadian Astronomical Society and the Hogg Lectures. This year we are indeed honored to have Professor Rob Thacker as our guest speaker, and with that I'll turn it over to the Dean, Stephen Smith, to introduce Rob.
Thank you very much. I'd like to start by welcoming everybody here tonight. It's fantastic to see so many people here on campus. So welcome on behalf of the university. We're very pleased to have the RASC General Assembly here, as well as to host the lecture tonight. I'm just here to introduce Dr. Thacker, who is Canada Research Chair in Computational Astrophysics here in the Astronomy and Physics Department, as well as the former chair. He maintains an internationally recognized research portfolio related to large-scale structure and galaxy formation. I understand the second part of that, but I'm a psychologist, so there's always a lot I don't get. He's a very accomplished science communicator, and as I'm sure you're going to see tonight, has the ability to take stunningly complex matter and explain it in such a way that really captivates people and gets their imagination going. So you're in for a treat tonight. He's a frequent subject expert. He's done, I don't think we could even count the number of media interviews he's done, TV and radio, as well as popular books and chapters. In addition to that, he's got 40 scholarly publications with over 4,000 citations, as well as over 100 conference presentations, proceedings, book chapters, all those sorts of things. He also has obtained over the years $1.7 million in research funding, and that's why he's a Canada Research Chair, one of the best in the country. As chair of the department, he was chair just after I started as dean. Great colleague to work with, very pleased to be able to work with him. Always looking out for the students, but also looking to better the university. I'm sure as many of you know, we have the new Ralph Medchuk telescope here on campus, which is the second largest telescope in the country on a university campus and the largest in the Atlantic region, and that's really because of the leadership of Dr. Thacker. He's a subject matter expert for local media. He's a talented teacher, mentor, and of course he's a member of the Royal Astronomical Society. His passion and extensive knowledge of the universe's mysteries has ignited the imagination of thousands of Canadians, and like I said, you're in for a treat tonight. Please join me in welcoming Dr. Rob Thacker.
Steve. Okay, I've got a level. All right. I have to do one thing, that everything is being carefully recorded, so before we start, I have to start recording. There we go, great. All right, hi everyone. Everyone doing okay? Chilling out, right? Science is not like eating your greens. Science is meant to be fun, right? So if anyone gets bored, in fact, I'm freaked out that Paul started with, the exits are there, all right? Right? But seriously, no, let's have some fun tonight. This is good stuff. And in fact, Steve said, I'm really an astrophysicist. I consider myself a completely amateur astronomer. In fact, I'm convinced that everyone in the Halifax chapter of the RSC knows the sky better than I do, right? But I come from a physics background, and I'm slowly learning more and more about astronomy. And so what I'm going to talk about tonight is something new for me, right? This is fun for me to learn all of this stuff. I mean, I know there are people in the audience who know more about spectroscopy. That's something technical, but there are people out there who know more than I do, so I'm learning as well, which is a great place to be. All right, so this is a difficult lecture for me to give, because I know that there are some members of the RSC who have quite a lot of knowledge about astronomy. And at the same time, this is a public lecture too, so I've got a talk that's kind of at a low level, but every now and again there are a few things where I do go into technical detail for members of the audience who can appreciate that. But if anyone has at any time goes, what are you talking about? Just put your hand up and ask, right? And I'll probably go, I have no idea, right? But it's okay. All right. So in the style of the famous Richard Feynman, who was a famous physicist who you either love or you hate, right? 3 easy pieces tonight. The why. I'm a big believer in explaining the why, because when I go and talk to politicians about funding astronomy, they go, why are we going to do this, right? So I'm going to start with why, right? And then we'll start with how. Now, at the moment, those words probably won't mean anything, but I hope that in half an hour they'll mean something to you, okay? And then we'll finish off with the what, and the what is how we're going to do this, really what is astronomy, it's not astrophysics in this case, right? and the new telescopes we're going to be building, hopefully, in the next few years. Right, well, my wife's mother-in-law is actually a paleontologist, and she said it shouldn't be called galactic archaeology, it should be called galactic paleontology, right? But I'm going to start with the definition of archaeology, and there may be some people in the audience who have an interest in archaeology, and traditionally, archaeology has been the study of human history, prehistory, through the excavation of sites and the analysis of artifacts and physical remains. And really, what does that mean? That means getting down and dirty, right? Right? And, well, galactic archaeology isn't like that, right? Galactic archaeology is completely different, right? So we think of archaeology as being brushing the mud off, troweling stuff out, and so on, whereas what I'm going to be talking about tonight is very different. I'm not digging beneath the feet, we're digging in the sky, right? So this is completely different, and we're going to be using things like this, giant telescopes. This is a Canada, France, Hawaii telescope, right? Really beautiful piece of equipment, although it's quite old now, 40 years old. But this is the kind of equipment we're going to be using, right? And I've got a joke. I've got one joke about archaeology, right? And, I searched so hard, right? But the problem with archaeology is all the jokes are dirty. Oh, at least you laughed. All right. Okay. So I'll start with the big picture, right? And it's so ironic that this morning, as part of the conference, we had Dr. Roy Bishop saying, well, I don't know about that dark matter and dark energy stuff, you know? So I'm actually going to start with dark matter and dark energy. It's what I study. And ironically, having worked in very, very highfalutin fields of theoretical physics where there's stuff that I'm really, whoa, I don't believe any of that, right? This I actually do have strong confidence in being true. So what am I showing you? This is a beautiful image, right? And this represents about 1/20th the size of the total observable universe. Why do I say observable? Because light travels at a certain speed, right? And we think the universe has a finite age, right? 13.7 billion years. So this is just this weird stuff called dark matter. It's really embarrassing to stand up and say that the universe is full. 85% of all of the matter in the universe is in some form, and we don't know what it is, right? It's almost, yeah, but we know it's there, right? We can see it influencing stuff. Either that or what we know about the laws of physics is really, really wrong, right? So, but this isn't just an image. This is a movie, right? So in fact, this is taken from a simulation, and we can create these virtual universes and solve the equations of the laws of physics, right? And now you can see that this is a beautiful three-dimensional structure, right? Very complicated, right? But all of the physics that is being solved in there basically comes out of the Big Bang and gravity, right? And we know this to really quite exquisite precision, and now when we go and observe the universe with telescopes, see where galaxies are, they have this kind of structure. This isn't an exact representation of what the universe is. This has all of the properties of the universe, but it's simulated within a computer. So that's the general kind of structures that we see. But what I want to do is now sort of show you how incredibly detailed that structure is, right? It's not just on that scale that you're seeing there. I'm going to go out now. This is about a quarter to a third the size of the observable universe. So if you put a few more over there and a couple more over there, then you get the whole observable universe, right? So what we'll do now is we'll zoom in. This was, again, simulated in the supercomputer, part of a big research program I was involved in a few years ago. Right, so now we can just zoom in, and you'll see more and more structure as you zoom in. Right? Again, this is just the dark matter. It's colored in a different way. We play lots of fun games with coloring dark matter because it really has no color. We just put that on there to make the pictures look pretty and have everyone go, ooh. Right? So this is actually, carrying on zooming in, this would be a cluster of galaxies. We see clusters, very, very rich clusters of galaxies with 300 or 400 galaxies in them. Right? And this would be the dark matter that's actually in that cluster of galaxies. Now, just as we get in on the next one, you'll be able to see lots and lots of points, and all of those points would be the dark matter that surrounds individual galaxies. There we go. Right? Now, each of those points you can basically associate with an individual galaxy. And we're just going to stop zooming in, but if we could keep on zooming in, we'd see the same kind of thing again. Right? And now we'll stop and we'll go all the way back out again. Right? But that's like the incredible structure you have from the larger scales all the way down to the smaller scales, and it doesn't stop there, of course. It keeps on going down smaller and smaller and smaller. So you have things within things within things within things, and we call that idea hierarchical clustering. Right? And that's a very well understood theory of the overall structure of the universe, and it seems to be really good. And in fact, those of you who are like interested in science and probably heard of something called fractals, yeah, this idea of this thing that as you blow it up, you can see the same kind of structure again, blow it up again. We kind of have a bit of that in the universe, but it's not perfect. There's a scale at which it doesn't work above and a scale at which it doesn't work below, right? But there's one bit in the middle where it's just right, and if you keep on zooming in, you see kind of similar structures again. Okay? All right, so that's how things look now in the dark matter, right? How did things get to be the way they are? And that's really what galactic archaeology is all about. It's not about what the things look like now, it's about what were things like in the past, right? So now I'm going to do another movie, right, where I'm going to show you how things evolve in time. And so some of you may say, well, doesn't the universe expand? Why aren't I seeing that expansion in your movie? We actually take that expansion out, right, so you can see what's happening. In fact, when we start the movie, it would be 100 times smaller than when it finishes, so you wouldn't be able to see anything, right? So I'm taking all of that scaling out, and you can just see what's happening. Come on. There we go. So immediately see the first things to form are small things, right? And what else do you see? A lot of mergers going on, things coming together, banging together in one another. More mergers going on, right? And you see things floating around outside other things too, right? Again, the astronomer's probably thinking, satellite galaxies. That's exactly right, right? And so now you have this beautiful structure, right, where you have a central region, and then surrounding that you have a halo of dark matter. So we call these things dark matter halos. Nothing to do with angels. And so you have that kind of beautiful structure. Want to see it again? Yeah? Okay. Oh, it hasn't finished yet. There we go. Okay. So, again, first things to form, small, merge together to form bigger things, keep on merging together to form yet bigger things. So that is, in fact, the time sequence of what happens in hierarchical clustering. And we think this is really, really very accurate. If we look back with telescopes, we can actually see a lot of evidence for this, especially with Hubble, but other ground-based telescopes as well. You may be wondering what this was a particular simulation of. The entire simulation goes on far, far larger scale than this, but this was actually meant to be the dark matter in the Andromeda galaxy in the Milky Way, and eventually the two of them will merge together. But we did this at UC Berkeley a while ago now, and in fact, the mass of Andromeda was estimated to be wrong then. So this simulation isn't quite right? But it still looks cool. Okay. All right, so I just want to summarize that for you, right? And this is hierarchical clustering in a nutshell, and this really matters, right? Because this is something we're going to be looking at in detail in galactic archaeology. That you form the smallest galaxies early on, right? Those small galaxies very quickly merge into bigger galaxies, right? And those bigger galaxies don't survive for too long before they merge into yet larger galaxies, right? And so that process, as I said, is supported by observations very well. The farther back we look in time, right, the earliest galaxy we see, really small, right? Really, really small. Okay? Yeah. It's smaller than we thought it was. I actually think it's even less than that now. They're almost the same. Right? So it's come down a lot. In fact, what happened was when we did all of our work back then, with all of the things that are around, because we made the galaxy so big, everything was moving too fast, right? Because we thought it was too big. Okay, and lastly, what have I done up there in the last one? I've put a disk right in the middle. Why have I done that? Because I want to show you that the galactic disks that we actually see, which are made of the stars, are much, much smaller than the halos, right? 10th, 20th the size, right? So galaxies extend in terms of their halo much, much further out. And I've got another picture of Andromeda, right, with the CFHT that goes very, very deep, and you can see that. That's in a few slides. All right. So that's how we think dark matter comes together and how it impacts the formation of the galaxy, right? But, of course, we don't see dark matter, right? We see stars, or we see the interstellar medium, right? The gas between galaxies glows, and so on. So we want to understand how that evolves as well. And, of course, we can simulate that too, right? It's actually very difficult to do. The physics of how dark matter interacts is just gravity. The physics of how gas evolves is something called hydrodynamics, which is much more complicated, much harder to do, much bigger supercomputers to do it. But you get amazing movies like this. Right? This is a disk galaxy. Don't worry about that funny blip at the beginning. That's just the person behind the curtain. Just kidding. So this is a disk galaxy, right? A simulated disk galaxy. And you can see the color coding just represents how dense the gas is. If it's more yellow, it's denser. And so where the gas is very dense, that would be clouds of gas that are forming stars. Right? And in fact, there are literally thousands of these very, very dense knots of gas. Right? And in fact, we see thousands of clusters of stars in the disk of the Milky Way. So we think this is actually a reasonably good representation. And look, it's doing something really weird. That's called a bar instability. Right? And this simulation is rather unique because most bar instabilities exist for a very long time. And this one is very transitory, and it will go in a couple more rotations. If you're thinking, why is it slowing down, that's completely unrealistic. That's just something that comes out of the simulation. Right? That's not actually what would happen in real life. It's just the way we've made the movie. And then at the end, you get something that looks like the Eye of Sauron from Lord of the Rings. But can you see it? It looks like it's still rotating around. Right? It's a really good optical illusion. Right? So what do I want you to take away from that? I want you to take away the fact that how everything is moving in the disk of the galaxy is really complicated. Right? Things are also bumping into one another within the plane of the Milky Way. Happens. And also, you can imagine, if things are that complicated, once you form something, how long is it going to survive? It's a big question. Right? How long did that represent? That's a few billion years of evolution. Right? It takes about 225 million years for the sun to go around the center of the galaxy. Right? You just had about a dozen rotations there. So this is a beautiful picture of NGC 3572, credit to ESO. Right? And why am I showing you this? I want to show you this because this is a stellar nursery. 20 million years old, there's probably slightly better estimates now. And what you're seeing is thousands of stars that have been born together from the same cloud of gas. Right? And these stars are going to slowly disperse over time. We see this happening. We see what we call open clusters. There are seen thousands of open clusters in the plane of the Milky Way. Right? So we know this is how stars form. Right? And we also know over time things are going to start moving apart. They're only very, very loosely bound. Right, by their forces of gravity. All of the red, right? Some of the astronomers will recognize exactly what that is, right? H-alpha emission, right? And that's from the giant molecular cloud, basically all the gas there being lit up by all of the stars inside, also pushing on it, pushing it around with winds. There's beautiful structures down here in the bottom right. I love these images, just fantastic physics. Like, it looks beautiful and it's got amazing physics. We also got little sort of like rings in there, things that are being lit up as well. There's just so much detail in that. Right. Okay. Let's have some fun. What I'm trying to convince you of is that galaxy formation and galaxy evolution is one gigantic blender. Right? And that sounds like a weird analogy, but it's completely true. Right? You've taken all of those things that have merged together and you've mixed them around, stripped them apart, and so on. Right? So, I'm going to show you how you blend a galaxy. It's a galaxy phone. Anyone seen some of these? The Will It Blend series? This is absolutely crazy. I just have to check my sound levels on this. Do not try this at home, please. Go on.
I'm going to press the starting bell button.
Right? So I'm just having a complete amount of fun with that, but I think you will now always remember that galaxy formation is a blender, right? So what we're really trying to do when we look at the galaxy now is to put it back into the same initial condition and figure out all of the bits that went in, right? That's what we're really trying to understand when we do galactic archaeology. All right, so I said I would have a picture of what the halo looks like. And we can do this very straightforwardly. It takes a lot of telescope time, but the idea is straightforward. And we can do this with the nearby galaxy Andromeda, M31, Messier 31. And so this was a project, and I'm pleased to say this is a Canadian project, led by Dr. Alan McConaughey at the NRC in Victoria. And so they did a very, very deep, looked at very, very low brightness regions around M31, and I said you can see how big the disk of the galaxy is relative to the halo, and there you can see, right? There's the disk in the middle, and there's the halo all around it, right? So the halo is big, right? Seriously big, right? But there's still a lot of structure. And here's a laser pointer I prepared earlier, right? Okay, so you have a stream of stars here. There's another one here. And there are others around here closer to the galaxy as well. And in fact, we know there are some of these structures around the Milky Way too, right? We just haven't, they're very difficult to see around the Milky Way for reasons I'll get into, right? But you can also see here's M33, right? Actual galaxies are really small compared to their dark matter, right? So there's a lot of stuff to see out there beyond just what we see in the disk. And if you're wondering, what, there's be like 3 or 4 full moons across that disk probably, maybe a bit more than that. Right? So this is quite a big patch of the sky, right? Several degrees. Right? But nonetheless, there's a lot of amazing structures here, right? And so that's what we see, and this is the kind of thing that theory predicts. Right? This is taken from a paper by Elsie Starkenberg in 2009, and she said, look, if we could look at all of the galaxies that came together and merged, what would that look like? Right? So we'll color code each galaxy as it comes in and merge, and we'll see what kind of picture we get at the end. And this is what she got along with her collaborators. Right? Now this is probably, sorry, I'm going to get all professional on you. It's probably not a really good model for the galaxy. It's a bit too smooth, and the way they did things meant things stayed together longer than they should. But all of this you would expect to be filled by stars that have been stripped apart and torn apart as they merge into the galaxy. So we think, nonetheless, that something like this is just sitting around outside the Milky Way, right? But the problem is, how do we go about figuring out what belongs with what and what came from what, right? That's the real challenge. And the other thing with this is, the sky is big, right? It's not like you're looking through a telescope at a really small patch of sky. You've got to look at the whole sky to see the halo around the Milky Way. So here's a movie that some of the members of the local RASC chapter may know. This is Jerry Black's time lapse from Peggy's Cove. This is Peggy's Cove down here. Okay, and I'll just take the lighting down. And this is the plane of the Milky Way, and even that is big. Right? I'll run it again. Sorry, I didn't take the lights down quick enough. Right? See there is the plane of the Milky Way. Right? Peggy's Cove. Boats. Okay? And we've got to look at the whole sky, right, to do this kind of stuff. So this is a real challenge. Right. So, there's a couple of ways that we can do this. We can go and look for these structures. Right? And the first thing we can do is just say, how are things moving? I have 2 slides with graphs. Okay? Right. This is one. And I'm going to do an Arnold Schwarzenegger impression as well. Right? But anyway, so this is velocity against velocity. What does this tell you? It tells you how things are moving. Right? And so if we find things that are moving kind of together, we think they're probably associated with one another. Right? So we can do this around the sun, and we've been doing it for a while, and we find a couple of notable structures. Right? There's something called the Hercules stream, right, which is obviously in the Hercules region of the sky, right? And that may or may not be associated with itself. The Milky Way is mean, right? It will do what's called orbital resonances. It will put things together and move them around together, even though they have no association with one another, right? It's really difficult to figure out whether things started together or whether they've just been pushed together by the Milky Way's overall motion. But there is another bit on here called HR 1614, and we know that that really does seem to be associated. It's all moving together. It probably all was one star cluster a long time ago. But these are very rare, right? There aren't very many of these. It's tough to do this in the disk of the Milky Way, right? You need something better, right, if you want to find groups that used to be in the disk of the Milky Way. It's good for the halo, though. It works in the halo quite well. So we need something better. Right, if we want to understand how the disk evolved. Remember I showed you that movie of the disk evolving and how everything was so complicated, right? And any CSI fans? Fingerprints, right? You need a fingerprint if you want to find the culprit, right? So we want some kind of thing that we can use to actually trace back stars to where they came from, right? And so this is our fingerprint, right? It doesn't look much like a fingerprint. Right, here's the second graph. Right, my Arnie impersonation is coming. Right, so what am I showing you? This is basically how much on this axis, and then this is the atomic number. It basically just gives you a really nice way of writing down all of the elements, and then it's just basically how much of each element do I have. Right, that's the one thing that we're going to use. Right, this is actually for the sun. Nearby star, we can do this really, really precisely. It's kind of difficult to do, and I'll just talk about that very quickly in a couple of overheads. But this is a real thumbprint for a star. How much of a given element does it have? Right? Now, those of you who know a bit about stars will know, hold on. Stars are constantly changing one element into another. They're giant nuclear reactors. So we've got to pick the right kind of elements if we're going to do this. Right? So let's pick the right elements. Right? This is the periodic table of elements in a form that some of you may have seen before. Most people have never seen it this way before. This is really cool, right? Where are atoms formed? Right? Where do we form atoms? So, those of you who've done a bit of physics will know that hydrogen and helium, they form in the Big Bang. Right? But things like lithium, beryllium, boron, they're actually created in space, or a little bit made in the Big Bang, but not very much. They're mostly created in space itself by, believe it or not, high-energy cosmic rays coming along and banging into hydrogen and helium nuclei. But carbon, nitrogen, oxygen, sulfur, neon, all of those elements are made in smaller stars. And then if you go to really big stars, the bigger the star, the more energetic it is, the hotter it gets, the more energy it can put in to create bigger and bigger elements. So by the time we get to large stars, look, anything with green on you can make in a large star. Right? But there's a few things you still can't make in a large star, right? And there's a few elements that are just made in supernovae, and there are these ones here, the view down here as well, right? And basically, there's about 25 elements that are kind of unique, right, in terms of once you form the star, they're pretty much the same throughout the lifetime of the star. Right? And so these are our sort of like holy grail elements to use in working out abundances. Right. So I just sort of said I would say something about how we make these measurements, right? We do this with something called spectroscopy. All atoms have their own energy levels and will absorb or emit light at specific wavelengths of light, right? So the astronomers will know this very well, right? This is spectroscopy. But here's the spectrum. This spectrum's really weird. Anyone see what's wrong with this? It's not the colors, but that's a great guess. It's a technical thing. There should be an H delta line there, but it's missing. Right? So this is meant to be hydrogen, right? But anyway, so we have the color, and then you can see these dark lines, and those correspond to the points in wavelength where the atom will absorb the light. So if we turned it around and said, where does it emit? You'd have red over here. This would, of course, be H alpha, and H beta, H gamma, and so on. Okay? That's just for the people who understand this stuff. Right? But we can turn that into a graph, and here's my Arnie impression. You know I said there'd be two graphs. I lied. Okay? There's going to be three. Okay? So here is the intensity of the radiation, and here's the wavelength. So we make this graph, but really, it's just a colorful spectrum, and we're plotting it as a graph instead. Okay? So for the sun, of course, we can do this in incredible detail. And here's just a tiny, tiny patch of the sun, right? A tiny, tiny patch, right? And there are lots and lots of lines, iron, titanium, more iron lines, chromium, magnesium, you name it, right? This is all really useful information, and you can build up an idea of what the precise state of the atmosphere around the star is, right? Because that's what you're measuring. You're measuring the outside of the star. And basically, my colleague, Dr. Ian Short, is an expert on this. I am certainly not an expert on this. Basically, the depth and the width of these lines are what you use to calculate how much of a given element is in the star's atmosphere or around the surface of the star. So that's what we do. It's very complicated, right? But the idea is now come to be known as chemical tagging, right? And really, a lot of people figure this out. Nowadays, things rarely are sort of like one person's idea. You often hear that several people had the idea at once. This is happening with Nobel Prizes a lot now. People are like, oh, well, I had that idea. That person had that idea. Who do we give the prize to, right? But I'm going to single out a couple of people who've really, really pushed this idea. Ken Freeman here, who's 74 now, but it's like the Energizer Bunny. He just keeps going and going and going. And Josh Bland Hawthorne. Oh, Ken is an Australian. Josh Bland Hawthorne was born in the UK, but works in Australia now. So the two of them have really, really pushed this idea, right? And they're doing a lot of work on this themselves. And so I'll just summarize this again for you. The idea is stars form in groups, and they form from the same gas. That gas has the same distribution of elements through it, so all of the stars that form in a group basically have the same fingerprint. Okay? Over time, because we use specific elements that don't change, they keep that fingerprint, right? But they disperse through space. So, what do you do? Go and look for stars that have the same abundances. That's it in a nutshell. Right? Just find the stars, match them up, piece together the old groups. Easy, right? You already know the answer to that one, right? So why is this a little bit dangerous for astronomers? Well, because we get a lot of mileage out of really beautiful pictures, right? Hubble Space Telescope has produced lots and lots of beautiful pictures. But we're now talking about doing stuff where you are not going to get a beautiful picture, right? You're going to get millions of graphs. How boring is that? Right? So this is the Pleiades, right? And what I'm trying to make clear to you is that each of these stars is going to have its own spectrum, right? And we're going to actually put a fiber optic cable on each of those stars in the focus of the telescope and take a spectrum. No pretty pictures anymore. Bit dangerous if you want to get money from the government. I'm just kidding, right? So instead of taking beautiful pictures, now the star is going to take literally thousands of spectra at a time, right? Not one slit, right? Some of you may be familiar with slit spectroscopy. Literally thousands of fibers in the focus, right? So no more fancy images from these particular telescopes that have those instruments on them. Okay. Right, so I said in the abstract, I talk about the pitfalls, and because I was joking at the time, I said, oh, we don't have to worry about black mambas biting us, or people coming along with whips and so on, right? Indy Jones references, right? There are a lot of technical challenges, right? And I'll try and make these fun by giving you the fingerprint analogy again, right? So the first thing that's really difficult is if things get spread too much over the sky, right, then you literally have to sample the entire sky, right, at really, really, really deep magnitudes, right? And that's very hard to do. That would take so long to do, right? So we want things to be kind of close together, right? And so that's a bit like saying, well, look, if someone's committed a crime and there are no fingerprints at the crime scene, right, that messes you up. Right? So we want the fingerprints near the crime scene, and we want the stars to be somewhat close together, not too spread out. Right? The second thing is the stars have to be similar. That's what I said about stars forming in a group having the same elemental abundances. Right? If they don't, right, it's a bit like going to one crime scene and getting one set of fingerprints, going to another crime scene, getting another set of fingerprints, another set of fingerprints, and they're all different. Right? Then you can't relate the person who committed the crime. And the last thing, it is kind of obvious, right? But if you're taking fingerprints with cellophane tape and it's just messing up every time you take the fingerprint and you can't get a good one, you can't compare one fingerprint to another fingerprint. So we need telescopes that take basically good enough abundance measurements, right? So that's about the best analysis I can give you. Trust me, I have condensed literally 150 pages of journal articles into 3 boxes, okay? But I think that gives you an idea. All right, so what's going on now? Now we're into the last part. How am I doing for time? Way over time already. I'm very sorry. If anyone wants to go, you can go now. All right? Okay. Oh, they're running for the exits. Okay. No, just teasing. So right now, the thing that's really incredible is something called the Gaia project. This is something that's been flown by the European Space Agency. And Gaia is truly incredible because it's taking positions of stars to micro arcsecond accuracy, right? Micro arcseconds. Right. How does it do that? Very sophisticated plotting of orbits in space. Very clever stuff. But it will also get an incredibly large number of proper motions, basically how things move across the sky, not moving in and out of the sky, but how things move backwards and forwards. And we'll get the true velocities of tens of millions of stars. This is really amazing. So I wanted to give you what's this like, right? I mean, I'm just giving you words. Well, you know Star Trek Voyager? Well, some of you probably know Star Trek Voyager, right? And they had the astrometrics lab, right? And they would go in there and they'd look around and like everything would be like, ooh, this is a really interesting piece of space, right? So Gaia is what we call an astrometry mission, right? You would take the data from Gaia and put that into the astrometrics lab, right? And then you could fly around inside it and stuff like that, right? So this is all about measuring stuff incredibly precisely, right? And we call that astrometry, right? So Gaia is a fantastic astrometry mission. So that will just tell us where things are, though, but it won't tell us about their fingerprints, right? These elemental abundances, right? So there are a number of projects doing this. In fact, there is one on the Very Large Telescope in Chile that's associated with Gaia, but I won't talk about that. I'll pick the one that Ken Freeman and Josh Bland-Hawthorne are running on the Anglo-Australian Telescope in the Southern Hemisphere, and this does 400 of those spectra at any one time. Right? Sounds pretty good, yeah? 400, yeah, we're going well. In fact, we'd look to put another 0 on that, right? 4,000 at a time. And this will measure 1 million stars, measure these chemical fingerprints of 1 million stars over 5 years, right? And you think, oh, wow, it's a lot of stars. How many stars in the Milky Way? Hundreds of billions, right? This is literally nothing, right? And in fact, there was a paper just within the last month that's come out that has really put a downer on people because we realized 1 million just isn't going to get us anywhere, right? We need way more than this, right? Even a factor of 10. We need a factor of 50, probably more than this, right? 4-meter class telescopes, which sound really big, are in fact comparatively small nowadays. But if you want to do things in the disk of the galaxy, they're actually pretty good for that because obviously things in the disk of the galaxy are, comparatively speaking, fairly close to us, right? And the stars are still bright enough that we can do it with 4-meter telescopes. But if you want to go out into the halo, remember I showed you that picture of how big the halo was relative to the disk, then you need 8-meter telescopes. And so there are a couple of projects coming soon. VLT Moons, someone gets a prize for a fun name, right? And so that will have 1,000 fibers, and that will operate on the VLT telescope. And then PFS, boring, prime focus spectrograph on Subaru telescope. The name of the telescope is better than the name of the instrument, okay? So that will have 2,400 fibers. So really getting up there, getting up to the 4,000 that we want to get to, right? But both of these will be operating around 2018, 2019, right? Pretty expensive to do. We're talking about $80 million to build the instrument. But this is because I meet with politicians a lot, right? Okay, they always say, why do you need more than one telescope? So you're all laughing because all of the amateur astronomers, I bet there's, who's got 2 telescopes? Put your hands up. Who's got more than 2 telescopes? Put your hands up. See, you understand, all right? Right? So you can't do everything with one telescope, right? And you really can't. And I'm trying to sort of give you an idea of how we do the best science and how I originally called this optimizing, but it's really how we do the best science. And the size of the telescope, right? Again, all the astronomers know this. The size of the telescope determines how much light you can get and how quickly you can do things, basically, right? Also, the field of view does that as well, right? How much of the sky do you see at any one time, right? And the only problem is, as astronomers very well know, the bigger the aperture, the more expensive the telescope, right? Professionals haven't figured out a way to break that yet, okay? So it's always a cost problem. But the other thing, yeah, I'll just do that, okay? So these 2 factors set how quickly we can do things, right? Obviously, you want to do things as fast as possible because we're competing against other teams. Right, we're competing against other countries, right? Science is competitive as well as collaborative, right? And then we have this box at the top, resolution and wavelength, right? That's how much of the spectrum do we cover and how well do we cover it, right? And you can all probably guess you want to do as much as you can with as much resolution as you can, right? Cost, again, right? But those 2 things determine the type of science you can do and the quality of science you can do. Right? Sometimes you say, okay, we'll just do low resolution across a big part of the spectrum. Other times you want to do high resolution in just one part of the spectrum. Right? So it's not easy to build one telescope that does everything. In fact, it's basically impossible. Right? You need a number of telescopes. But you didn't need for me to argue that, did you? You all got that? You can't have just one telescope? Okay. So what is unique is that until now, no one has really considered building an entire spectroscopy unit and an entire telescope together to make them one cohesive unit, right? And that's what we're looking at doing in Canada right now. This is a project being led out of the NRC in Victoria again. A number of people there, I'll just mention 3, although I will be doing some people short, I'm sure. Dr. Alan McConaughey, Dr. John Hutchings, and Dr. Patrick Cote, right, have been pushing very hard on this. There's a number of other people as well, right? But those are the people who I interact with most anyway on this idea. So this is the Canada-France-Hawaii telescope on Mauna Kea. And some of you may be aware of there is considerable uncertainty over the future of Mauna Kea right now because it's considered sacred by a number of native Hawaiian groups. I don't want to say anything about that. I'm not an expert on that at all, right? And I defer to the people who are out in Hawaii on that. But basically the idea is to replace the current 3.6 meter with a big honkin' 11 meter telescope, right? And it's bigger. How will it fit, right? Well, it just turns out we completely over-engineered the CFHT when it was built 40 years ago. The pier supports, again, something for the astronomers, an equatorial mount, but we don't need to build an equatorial mount anymore. We can build an LAS, right? Which is much lighter, even though the telescope itself is much bigger. And so you go from this to this, right? And it all fits, right? And it has to fit, right? Because one of the things that's going to change in the Mauna Kea management is that you cannot make an observatory more than 5% bigger than it was in the past, right? So this is what we're planning to do. And this is a great idea. And in fact, I'm leading a national review of astronomy right now. We sat down and basically have promoted this as one of the projects that we think Canada should actively invest in. It won't just be Canada. We're probably trying to get at least 5 or even 6 possible other countries involved as well, right? Oh, something for the gearhounds. The ray diagram, right? So what are we looking at? Again, sorry, this is technical for the astronomers, right? It's Cassegrain, probably, right? There's a reason for that we can actually, we're worried about how the center of mass of the telescope moves, right? Sorry, this is all technical stuff just for one overhead. And so with a Cassegrain alignment, we can actually put a lot of the heavy stuff in here, and that will keep most of the weight over the pier, right? This is a little bit non-traditional, but it will work. 12-meter nominal diameter. When you take out the central obstruction, it's about 11.64. And here's the really incredible thing, that the field corrector will have 1.4 meter lenses in it. Right? Trust us, the glass is strong enough for that. Right? No, yeah. Yes, it will be segmented as well. Yeah. In fact, the segmentation is the reason why we can't go even faster than that. Right? So, although in fact, for technical reasons, going faster than that wouldn't do much help anyway. So, and this comes back, the thing down here. So I'm trying to show you, if you were to look through that telescope, imagine look through it. Here's the field of view of the MSE telescope, and here's the field of view of the 30-meter telescope, TMT, because I did a radio interview with Rick Howe on Monday, and he said, well, you're just getting $250 million for the 30-meter telescope. Why can't you do it with that? Right? And it's right there. Right? You just don't see enough of the sky with TMT to use it efficiently. TMT is designed for seeing things that are like way off. Right? So it's designed to see small things. Right? MSC is designed to see a lot of the sky at a time. Right? Over 2 full moons. Right? Right? So this is a big telescope and it has a big field of view. Right? So it's a great idea, and I'm really hope that we can get enough money together and sell it well to the government. Right? So, I'm now about to wind up. Oh, wow. Okay, I'll go really quick. Okay, so the future, where are we going to figure out more things other than just looking at the sky? Because the fact of the matter is, I'm a theoretician, right? But I rely upon working with observers. They're fun and they're quirky, right? But we work really well together, okay? So I've got to up my game as well as them upping their game. So I've got to come up with models that better explain how we get star formation. I've got to come up with higher resolution disk models, because those ones that I showed you really aren't that good, even though they look really cool. There's a number of things that are missing from them. And we've also got to look at how things are forming basically in the entire universe, not just doing them isolated from everything else. Right? And that's a challenge. That needs a lot of computing to do. Right? But we know what we have to do. Now it's just noses to the grindstone, do that hard work. And at the same time, the observers, well, it would be great for us to know more about what's going on in the halo, knowing more about those streams of stars and so on, and also where the first stars are. Right? That's an important thing that could go into our models as well. So everything works together. Right? You can't just do everything with a telescope. You can't just do everything with theory. The two of them have great interplay. Right? So this is my last slide. Sorry, I've run over. I apologize. I hate it when people run over. I'm very sorry. Okay, so by 2030, right, that's the one bad thing that I'm always accused of. Everyone's always saying it's always 10 years away. It's 15 years away, right? But I think what we'll know by 2030 is really, really incredible, right? The first thing, we're going to know the structure and the origin of our halo to incredible precision, right? Right? It won't just be, we'll probably be making diagrams like that, right? But they'll be real diagrams of the data we have. We'll have found the oldest stars in the Milky Way, right? I can't say we'll have found the exact oldest one, but we'll have found all of the oldest ones. Right? We'll also have found hundreds, and I put a question mark on there because I'm a scientist. I want to be honest about uncertainties, right? There is a lot of technical detail still to be worked out, but I'm fairly confident we'll find hundreds of former stellar groups that evolved in the disk of the galaxy. And from that, we'll have an amazing knowledge if we bring in all of what we're going to learn from Gaia about the dynamics of our Milky Way and how everything is moving. I mean, it would be mind-blowing, right? Absolutely incredible. All right. Thank you to everyone in the RASC chapter of the RASC for a great GA General Assembly, not Galactic Archaeology. Thanks, everyone.
I will ask you one quick question
Sure.
before we say thank you, and that is, can you explain the shirt?
Oh, I'm terrible. Oh no, I'm so embarrassed I didn't do that. Oh, okay. So thank you, Paul.
No problem.
So this shirt, oh, I'm so embarrassed, was made by a lady called Ellie Zupko, and it's a celebration of 50 brilliant female scientists, technologists, engineers, and medical doctors, right? And I don't want to go into too much of the detail. You can look it all up on the web. If you search the Twitter hashtag #thatothershirt, all one word, you will see all of the details. But astronomy in particular is very male-dominated, right? And us as guys need to act in a way that doesn't discourage women from coming into our field, right? And I've grown up with two sisters. The person that I was always fighting to be best with at school was a woman as well. I've never had any thoughts that women were less capable of stupid rubbish like that, right? So I'm completely happy working with women, and I want women there. I don't like it when I'm sitting in a room full of guys and I'm thinking, there's a viewpoint we're missing here, right? So I want more women in astronomy. I'm going out, talking to people, trying to encourage people, and I'm really, really happy to say that we have a lot of women coming through in our undergraduate program. The problem we seem to have, right, and I'm going to get political on you, but the problem we seem to have is that they get through undergrad, they get into grad school, and then there's a drop-off, right? And there's also a drop-off in women being in senior positions as well. And this is not good. This is not good for us as a society. This is not good for science, right? So we have to do something about this, and we have to understand why it's happening. And it's not clear that it's just guys being really sexist. There are some really weird biases that go on. Women can sometimes be biased against women, right? And there are things that we need to understand to address this, but we will. And so, yay, sure. Okay.
Thank you, Rob.
Thank you.
On behalf of the RESC nationally and our center here and the General Assembly, we have a small token of our appreciation for you. It's one of our fleeces and one of the dream catchers from the Mi'kmaq who are presenting to us tomorrow night with the drumming at our banquet. So
Thank you very much.
Thank you again, and
Thanks very much. And if anyone wants to ask me questions offline, please feel free.
thank you.
And have fun. Science is fun. It's not like eating your greens. Science is awesome.